Hello, my name is Teodor Tchalakov from the University of Illinois at Urbana-Champaign, and I'm excited to share with you my risk research on guaranteed parameter uncertainty estimation using interval analysis for robust safety critical control, a device by Dr. Chin Lin and Dr. John M. Dolan. We are looking into guaranteeing safe control of systems with uncertain models. Currently, a control barrier function quadratic programming controller is the most common controller used for safety control. However, it requires an accurate model to be provably safe. Recent developments in robust safety critical controllers have proposed robust control-no function control barrier function quadratic programming controllers that provide theoretical guarantees on stability and safety under bounded model uncertainties. However, they suggest that the controller's response to uncertainty be manually tuned. So our question is, can model uncertainty be found through data, and can it be solved for in a guaranteed manner and done online? Our proposed approach is to solve for the feasible parameters in a guaranteed manner from observations using set inversion via interval analysis, and then to use interval analysis to formally solve for model uncertainty bounds and apply the largest uncertainties to the robust CLF-CBF-QP controller. To understand the effects of uncertainty, consider a control affine nonlinear system. Our true model has an input-output linearization of mu, while our nominal model has an input-output linearization of mu with these extra uncertainty terms that relate the uncertainty from a true and nominal model. Now, as these uncertainties go towards zero, then our nominal model becomes our true model. And they can be solved for in the following manner. However, to solve for the largest uncertainties, we want to apply the concept of the minimal inclusion function from interval analysis, where, for instance, sine of x, the inclusion function from 0 to 2 is 0 to 1, as it includes all of the outputs from that interval. Likewise, from 1 to 5, we get negative 1 to 1. This can then be applied to solve for the delta values given a set of feasible parameters. To search for these feasible parameters, we can use the set inversion via interval analysis algorithm to perform this parameter estimation, where we search a parameter space bisectively by using boxes and comparing the boxes in the parameter space to their transformation into the observation space. There are two cases that can appear where we start and where we continue and also stop the search. We will continue the search if our parameter space results in an undetermined green box that is partially within the dataset space and partially outside. Otherwise, we will stop our search in a region if our parameter space is fully within or fully outside of the feasible parameter space. To take a look at this uncertainty estimation, we will use an adaptive cruise control scenario where an ego vehicle is trying to go towards a lead vehicle while maintaining safety, assuming a headway and the ability to brake if the lead vehicle slows down. However, in this model, we don't know the mass of the car and we don't know the friction that is responsible from the wheels. So SIVIA solves for this by providing this, for one observation instance, a red band that is our set of feasible parameters, which are the result of measuring the input to our system, the velocity and control, and then assigning them bounded uncertainties, and then comparing this to the acceleration, which also has a bounded uncertainty. Then, once we have two observations at a minimum for this example system, we can make it determined and see that we have the intersection of these two observations, which results in our feasible set of parameters given our observations in a guaranteed manner. However, the drawbacks of SIVIA are that it is slow and it does not iteratively update online, and it requires checking each box, which is against the entire data set of observations, which can be expensive online. So our approach to improve the efficiency of SIVIA is to find the smallest box that contains all of the feasible parameters inside of the parameter space. So SIVIA will normally solve for this red region here on the left, but our bounding approach can solve for the box that contains this region while only having to solve the boxes that are required to create this large box. So we can skip all of these white areas here, as we know that they are already within the box that we are searching in, and the box is growing, so we don't need to continue searching within that growing box. Then we explore using heuristics to motivate the search for the farthest boxes that we want to use to grow our box. So we can use various system identification approaches. And we evaluate these heuristics by taking an L2 norm of the difference of the center of a box that we're using to guess from SIVIA normally and the system identification guess. Likewise, we also looked at using just the volume of the box. Our results show that having no heuristic on SIVIA normally is slow compared to adding a heuristic and using the bounded approach. However, this rate of solving for a 2D case is still not real time, so it will require more research into the future. But what we can see is that if we apply this to an adaptive cruise control scenario, given a nominal model to our system and a normal nominal control, we can see that the robust version can track much closer to the velocity of the lead vehicle, and both the robust and the nominal controller, using the bounds that are found from our bounding SIVIA approach, still enable comparable safety to our nominal baseline. For further investigation, we want to test this on changing model parameters and a physical system to experimentally validate our approach. Likewise, we want to investigate speeding up the search using more advanced grading techniques. And we also want to look into using neural networks to learn the parameter mappings for observations, and then to combine them online to reconstruct these feasible sets. And we want to go from boxes to more general set representations, such as polytopes, zonotopes, and polynomial zonotopes. I would like to thank my advisors, Dr. Chin Lin, Dr. John M. Dolan, for helping me with this research, and to help Rachel Burchin for organizing and working with everyone at risk to make this a wonderful experience. And I would also like to thank our mentors and sponsors as well. Thank you.